Our next talk is going to be Jim Cutts, talking about subcloud imaging of the surface of Venus.
Thank you, Noam. What we're talking about here is the concept of imaging from just below the clouds on Venus. Why would we want to do that? Well, we know we can do nighttime imaging, either from orbit or during flybys at Venus. We've seen it from Earth. Problem is that to do it from orbit, surface thermal radiation must get through an optically thick light scattering cloud layer between 50 and 70 kilometers in altitude. And this degrades the this degrades the spatial resolution of the images to around 100 kilometers. This problem is fundamental. It's not something that'll be fixed by future missions with better instruments. And so we've been looking at the scientific and technical feasibility of acquiring near-infrared nighttime images from below the clouds. So first off is, why would we want to do this? Why is it important to have resolution that's better by about a factor of 10 to the 4? On the left side, you can see an image that's been shown many times at this meeting already of a volcano, and the information in the infrared is of much lower resolution than the underlying radar image. And so, there's something different here. There's an enhancement of the emissivity, but you don't know what's causing it. The picture on the right shows what you might do if you had 10-meter resolution. This shows a series of lava flows on the west side of the island of Hawaii. And if you look closely, you can see some are very dark, which would mean high emissivity because there's a visible image. Some are much paler, and those would be older. And so you'd be able to see this sequence and really prove what has previously been speculated. So not only can you do something with emissivity, but you can also learn if there's active volcanism with a much higher level of confidence. These are a couple of images taken at different resolutions of Augustine Island in Alaska. The upper one has a resolution of 1 kilometer. The lower one has a resolution of 100 meters. And you can see on the upper one, it looks like a fuzzy blob. Maybe it's an enhanced emissivity, but you can't really tell what's going on. Factor of 10 resolution breaks that up into individual spots, so you know those are active sources of volcanic activity. So how can we realize this objective of achieving much higher resolution from operating below the clouds? So we've divided this up into 4 issues. How well can we image the surface from beneath the clouds? And specifically, what are the limitations here? And primarily, the Rayleigh scattering of the very thick atmosphere. But we also need to consider the subcloud haze. And then if all of these things look good, what sort of implementation would be possible? We've drawn on the data from the cloud particle size spectrometer, the Pioneer Large Probe, to base our knowledge of the clouds and the subcloud haze layer. This is a little complicated here, so we've simplified it into a model. The shaded area shows the clouds, and the pinkish outline shows the subcloud haze layer. And that's composed of a region between 50 and 45, which is fairly dense, and then below that from 45 to 30, much more tenuous. And our platform, we expect to be more or less in the middle of that somewhat more dense haze layer. This is the geometry of what we're looking at here, and this has been embodied in a model that has been developed by Anthony Davis, who's the senior author on a paper that's hopefully going to appear in press very shortly. It's in final review, I think. And his model incorporates many of the processes. In fact, some of those that Jada talked about earlier, where it deals with reflections between the lower surface of the clouds, which of course are as bright, as highly reflective, 80%, as the top surface that we see from above. And so this is quite a sophisticated model that has been put together. We compare this model here in this chart, and I'm not going to go through the details of this, with other models that have been developed over the years. And the one I want to emphasize most is the first one back in 2002, where Morose did this for the first time and came up with some answers that are not too far from where we are today. Davis et al. Published a paper in 2020, but that paper didn't include the effects of the haze. It didn't include emission from the lower atmosphere, which affects some wavelengths, but not others. And it didn't affect this backscattering from the clouds. All of those have now been incorporated. So these are some of the highlights of the results. And again, I'm just going to compare the Morose results with those of the Davis et al. So Morose found that the contrast ratio, if you just consider the Rayleigh scattering from the atmosphere, and this is a very thick atmosphere, realize, in this case, at 1.01 micron, the contrast is 30%. That's the loss in contrast you see for an image of the surface. Our initial estimates of that in this paper, Davis et al. Paper, were 42%. So we thought at first that it was somewhat better than what Morose had done. But then taking these other factors into account, that's dropped down now to 24%, so a little worse than Morose. The other key part of this was the haze and the effect of the haze. And so we modeled that based on the results from Pioneer Venus, and we've taken a sort of a worst case assumption of a factor of 10 beyond what was seen there. Morose, on the other hand, relied for his haze estimates on some of the Russian results, which we think are a little more questionable. So in this case, what we find is that there's some additional loss in performance because of the haze degradation, but it's minor. And so at 21% contrast, we still think that there's imaging, we can successfully image the surface. Although it should be understood, we have high resolution, 10 meters, a factor of 10 to the fourth, better we can do from MORBID, but there will be a contrast loss, which you don't actually see in the orbital image. So how might we actually implement this? So we've looked at three concepts that could do this repeatedly. The challenge here is that in this region of 47 kilometers, the temperature is about a little over 100 degrees, 110 degrees. So you can't stay there permanently if you want to work with conventional electronics. And so each of these concepts involves dipping down into that layer for a while and then going back, cooling off. The one on the left is doing this with a balloon that would dip down and is designed to tolerate that environment. The one in the middle would rely on the kind of balloon that Paul Byrne will be talking about later this afternoon, that would then lower this tow body on a tether down into this region. And then the third one is a drone, which would moor with a balloon, descend and return and dock. So these are the concepts. Now, we should also point out that if you don't demand that you do this repeatedly, there are simpler ways of doing that with probes that would be just sort of one-off imaging, more like what Da Vinci is doing, for example, for its surface imaging. So just to wrap up here, from orbit, scattering by the Venus cloud severely degrades the spatial resolution of near IR nighttime imaging. So imaging from below the clouds at 10-meter resolution is feasible and would greatly assist geological interpretations, including identifying active volcanism. The Rayleigh scattering degrades the contrast of subcloud images. The latest models indicate that 24% of the contrast will be preserved in images at 1.01 microns. The subcloud haze at the levels identified by the based on the Pioneer Venus probe mission data will have a further modest degradation. As I mentioned, there have been reports of higher levels of haze, and that they would, if that were true, they would have a great impact. And so then finally, we have these three options for acquiring subcloud images that would enable multiple sites to be observed in a single mission, and then simpler concepts would just provide for one. Thank you.